Hi everyone, welcome to GemChem. Now today's video is on group 13 elements, and here we are going to deal with group chemistry part 7 video. Now see here what are the topics of discussion: boron nitride, synthesis, structure, bonding, lithium aluminium hydride and sodium borohydride, and trends of halides of group 13 elements. Now before starting, already 6 videos are uploaded in channel. You can watch it. I will give the link in the description box as well as the I button present about this video. And if you are new to GemChem, do not forget to subscribe the channel and hit the bell icon for regular updates. Now let us start. So first we will discuss about the synthesis of boron nitride. Now boron nitride is Bn, right? So it can be synthesized from borax using NH4Cl. Now what is borax? Borax is actually Na2B4O7. Now how it is prepared? Let us see. So Na2B4O7 on reaction with 2NH4Cl and fusing them together, we get 2NaCl plus water plus 2B2O3 plus 2NH3. Next we will react this B2O3 and ammonia to form the boron nitride and water. Now you have to see here carefully that this reaction is reversible, as a result of which we get Bn plus 3 water, again B2O3 and ammonia. Now this on being reaction in presence of the water as well as high temperature, we get BOH whole 3. Now we will see the structure. Now if we consider the structure, it is somewhat hexagonal in structure and there is layer after layer formed one over the other. So this boron nitride consists of layer structures where each layers are made up of hexagonal units, and these hexagonal units have alternate boron and nitrogen atoms. The edges of hexagon are being shared by two different hexagons. So if you see, this edge is being shared by this ring as well as this ring, right? And the boron nitrogen distance in a particular layer, if you consider, is much shorter than this boron nitrogen distance in the two different layers. So we can say that there is a possibility of pi cloud delocalization in each layers. The layers are stacked over one another in such a way that the hexagon are eclipsed on one another. The nitrogen atom of one layer lie directly above the boron atom of the next layer and vice versa. The layers are held together by van der Waals forces. Okay, now we are going to deal with the bonding portion. So in bonding, we need to first draw the orbital picture and then show the box diagram. So first, see here, what is the configuration of boron? It is 2s2, 2p1, right? So let us draw the box diagram. Here is our boron and here we are going to draw 2s with the electrons present 2 here and 1 here. This is our 2s and this is our 2p. And if you consider, this is the ground state configuration. Now we are going to deal with excited state configuration. So see here, one of the electrons from the 2s will go to the 2p, right? So here one, here will be one, here will be another. So this is my excited state. This is 2s and this is my 2p. Now these each single ones will bond in a sigma bond fashion with the nitrogen to form the bonding in the boron nitride. So this is nitrogen, and this is nitrogen. Similarly, in case of our nitrogen, we have 2s2, 2p3, 2s2, 2p3. So this is a normal ground state, but whenever it is excited, then we get it as 2s1, 2p4. This goes at the back side, and if you consider, these will undergo sigma bond with boron, right? And from here only we can understand that there is a sp2 hybridization in this case, as well as in this case there is sp2 hybridization, right? So we can say that it is evident from each of the nitrogen atoms which contains filled p-pi orbitals to donate the pi electron density to the 3 adjacent vacant p-pi of 3 boron centers, and thereby this leads to some amount of delocalization. But in case of graphite, just similar as this one, this delocalization is much lesser. Now our next topic of discussion is that boron is often referred to as inorganic graphite. So why this is so? We have already seen the structure of boron nitride and we know the structure of graphite, right? So this boron nitride has layer structure like graphite, where the layers are made up of hexagonal unit. And if you consider for the graphite, there is a hexagonal unit of carbon, while for boron nitride, the hexagonal unit is consisting of alternate boron and nitrogen atoms. Now if you consider the structures in boron nitride, we see that the hexagons are eclipsed over one another, but for graphite the stacking is such that they are staggered. Okay, and finally what we can say is that due to these similarities in structure, there is also similarities in some physical properties like melting point, slippery to touch. As a result, we can say that boron nitride is inorganic graphite. Now we will start with our second topic of discussion, which is the lithium aluminium hydride and sodium borohydride. So from here only one important thing is that which one is the stronger reductant. So if we draw the structure of these AlH4 minus. So how to draw the structure is already being shown in the bonding videos. You can watch it. I will give the link in the description box as well as the I button present above this video. Now we have for aluminium 3 and for 4 hydrogen atoms 4 and 1 for the negative. So we have 8. This 8 is for tetrahedral structure. So we can draw it like this: lithium plus and aluminium with 4 hydrogens in the tetrahedral positions, right? And we have a negative sign. Similarly for BH4, the structure will be more or less same. If we try to draw, it will be same. It will be 8 and the structure will be B in the middle, hydrogen in the top. Here is one other hydrogen, another hydrogen, and finally we have a hydrogen here, which is negative boron, and a sodium plus. So from here we have to judge that which one has the weakest hydrogen bond with it. As a result, what will happen is that it will release H minus, and this H minus is actually acting for the stronger reductant, right? So first we will consider here aluminium. We know that the size of aluminium is much greater than boron, right? So if the size is much greater, then the bonding with the hydrogen will be weaker because it will be easily cleaved, as a result of which we can say that aluminium hydrogen bond is weak and cleavage is much favored. Secondly, if we consider lithium plus and sodium plus, lithium plus being smaller in size, we can say that it can easily polarize AlH4 minus. But in case of sodium plus, it is larger. As a result, it cannot easily polarize the BH4 minus. So we can say that aluminium hydride bond is much weaker and it can easily release H minus ion. So as a result of which lithium aluminium hydride will behave as a stronger reducing agent than NaBH4. Now we will skip on to our next topic of discussion, that is strengths of halides of elements of group 13. So in this case we need to consider one important thing, that is these strengths can be discussed in a following pattern. First we need to know about the types. Next we need to know about the reactivity, and the final one which we need to know is about the structure. Now structure of halides more or less we have already done, so more emphasis will be given on the types as well as the reactivity. So for boron, the type of halide which is generally seen is that BX3. But for the other elements, if we consider aluminium, gallium, indium, we see that these forms dimer like Al2X6. For gallium it is Ga2X6, and for indium it is In2X6. And if you consider for thallium, it will be different from the others, TlX. Now, the trihalides of boron are monomeric since there is an electron deficiency at boron center, and these are reduced by delocalized p-pi back bonding. But in these cases, since the sizes are much greater, this p-pi back bonding is not favored. As a result, they undergo dimerization in the form of 3-carbon 4-electron bond. Now if we go for the reactivity down the group from boron to aluminium, we see that there is a dimer formation. As a result, since there is a dimer formation, there is greater number of bonds, and in a reaction the bond breaking always occurs. So for the reaction to take place here, more number of bonds has to be broken, as a result of which the reactivity decreases from boron to aluminium. Similarly, from aluminium to downsides also, the lattice goes on increasingly becoming stable, as a result of which there is a further decrease in reactivity. Right. Now we will consider the structures. So if you first consider the structure of BF3 in general, then we have boron in between and the fluorines like this in the 3 sides, trigonal planar, right? And the orbitals are like this. And since we have already seen that there is a p-pi back bonding, so it will be like this. Similarly, it will be like this, and the direction of donation will be like this towards the boron being electron deficient. And the structure of Al2Cl6 is already been done in the previous video, so do watch it in order to understand the structure. And the other two, that is gallium 2X6 and indium 2X6, is similar to that of Al2Cl6. So this was the topic of discussion for today, and in the next video we will deal with the group 14 elements. So hope this was helpful. Thank you for watching. Do not forget to like, share, subscribe and comment.